moment of area. Okay, we will learn this. Okay, I will teach you all more into detail of this. This one is easy. Okay, just my over I m. I will teach this in week 3. This is week 3. Week 4 is week 5. Week 6 and week 7. Okay, week 6 and week 7. We're going to do 3D. Okay, bending moment or moment in 2D and torque in one direction. Okay, right. The second mode of failure is due to shearing stress right? Shearing stresses due to the load P. Okay, due to the load P. So what we're going to apply, okay, I'm going to write out the formula first, okay? So the shearing stress is equal to PQ over IT, okay? And where Q is the first moment of area, and T is the thickness of the beam. Okay. Then some of you will ask me, Eugene, the force is applied on P, right? If you look at the force is at P, is acting on this surface, which I'm going to highlight, is acting on this surface, as you can see, right? If it's acting from this surface, this is 90 degrees, right? The force is 90 degrees to the surface, right? So when that's the case, why? Okay, so if this is the case, why, right? This is known as shearing stress. Yes or no? Right? You are curious now, right? Eugene, the normal stress is force divided by perpendicular area, right? That is perpendicular. So the P over here will apply the stress on this surface also. Yes or no? Right? So this, in fact, the blue is in fact the shear stressed surface. Right? The one I highlight in yellow is perpendicular, right? The one I highlight in blue is parallel to the force, right? So by right, it should be that blue surface, right? But why failure will occur perpendicular to the applied force? It's interesting, right? So let me make things easier or explain in a better way. So if I draw an element, okay, now I draw an element, right? The force P is acting down here, and then you have a stress, okay? You have a stress. So if we were to follow the P over here, okay, there's a shear stress, okay, shear stress, okay. The intersecting plane is the x axis, and the applied force is in the y axis. This is how you label them. Okay. So over here, let me explain you the x represents the intersecting plane. The y is the applied force direction. Okay. The y is the applied force direction. Okay. Now, so this over here, the shear XY represents the blue surface over here, and the blue surface is over there also. But why, right? Why it has anything to do with what has to do anything to do with the yellow surface? Okay, let me elaborate why the yellow surface is important. Okay, so let's look at the failure due to deformation. Okay, let's look at the failure due to the deformation. So I'm going to draw how this structure will deform. Okay, I'm going to draw how this structure will deform. So it's still a cantilever beam, right? So the structure will deform this way. Okay, I'm going to do this. Okay. The structure will deform this way, right? And each layer, so I did how many layers? 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. This always the last one, giving me problem. 4 and 5. Yes. I will. Okay. Right. So what you will see, so same transformation, X, Y, rotation. So when you bend, this is a schematic, okay? You can't see this visually, okay? It is amplified, okay? So what you see is there is a change. There is a gap, right? Right? You can see there's a gap over here, down here, there is a gap, right? And you realize that if the structure is not the gap is in the what? X direction, right? If this is the undeformed, the gap is in X direction. This is deformed, so that is the gap. Okay. So now, why? So I'll highlight over here the delta. Right, the delta is a shear strain. Okay, it's a shear strain induced by the shearing stress. Okay, by the shearing stress. Okay, so the failure is in fact perpendicular to the applied force, yes or no? Because the change, this distance change, okay, the change in this direction. So I'll okay, my bad. Okay, so I'll call this the change in X. This is the change in Y. The change in Y is not a lot compared to the change in X. So why is that? Okay, or why? Okay, why we calculate the shearing stress, right, on this surface? Why we calculate the shearing stress on the blue surface, right, on the blue surface, and we are able to relate to the yellow surface. Okay, to the yellow surface means to the yellow surface. Okay, so why is that? So this is because, okay, this is because in shearing stress, right, the element has to achieve equilibrium. So what do I mean by that? Okay, what do I mean by that? So if this is our element, right, this is our element, and this is our transformation, okay, and this is our applied force in Py, right? So over here, we know that this is shear XY direction, right? So now with just one stress, the element will what? With just one stress, the element will rotate. So we need something to counter, yes or no? So to counter, we put another shear over here. So this is our shear. The intersecting plane, so this surface over here, right? This surface, which is the yellow surface over here. The intersecting plane is in the Y direction. The force applied or the direction of the arrow is in the X direction. Okay, so this is what we mean by equilibrium. Okay, so to complete the diagram, this is how the shearing stress will behave. Now we will be dealing a lot of this in after the term test. Okay, term test, we'll be dealing with a lot of this, and this is where the blue surface is, right? So that is why the yellow surface that I shaded in highlight in yellow will fail. Okay, we know that the blue surface, the change in length is going to be very small. It's the yellow surface that the change in length will be great. Okay, so now this is what we call, I'm just going to put this term in, you don't need to remember this. This is what we call negative shear. Okay, and we look at negative shear. I'm going to draw in orange the deformation pattern. Okay, the orange, and this is our deformation pattern. And some of you might ask, how do we get that deformation pattern, right? So this is our, so how do we get this deformation pattern? We get this deformation pattern, okay? So I want you to put both your left fingers, right? Your left fingers on this side of the square, okay? And your left finger. I know this is difficult online, okay? So these are your left fingers on the end of the square, and I want to put your right fingers, your two fingers, okay? Your two fingers means these two, you all can see me, right? These two fingers, okay? So this is your right fingers, and I want you to, let's say the element is flexible, and I want you to squeeze them, okay? So when you squeeze them, the deformation looks like this, okay? Does that make sense? Okay, so when you squeeze them, the deformation. Now I'm going to draw for you positive shear. Okay, I will explain to you probably when we do mole circle why is it positive and why is it negative. Okay, so positive shear, it goes the other way. Okay, so positive shear, it goes the other way. So this is positive shear. Okay, and then I'm going to again sketch the deformation pattern. So this is our deformation pattern. Okay. Some of you probably have seen this before, some of you not, but I want you to know now. Okay. Okay, so that is our deformation pattern. Okay. So for this topic, before I go on, anyone has any questions?